Yeah, so remember now, yeah, so as I say, I was just recapping, showing you how to find the area of each section I had the total. So here, so the distance, as I said, here would be 4r upon 3 pi, whatever that work out to be coming right down. And the center of the circle would be the circle, y bar, part of it, distance would be the radius, right? See it here? That distance there r coming down to the center, but it need to come to the origin. You always have to map it to the origin. So where am I? So when you map it down to the origin, trying to get back to this page. When you map it down to the origin, it's going to be 5, right? For that one. And the x bar, as I was saying, for all of them, it's going to be 1.5 because it's the center where the radius is. So that is r. So all of them is going to be your r. And this is the same distance from here to here. Still, all of them 1.5. All right? All right, so let's look at it. All right, so right around here, the first part, we said we would find the mass. You need to find the mass to get the conversion. So now, one of the things you need to do, you see you can approach it this way. You don't have to. The thickness is 1.05 millimeter. You can convert that to meter if you so desire, right? And it will be in 1 meter upon 1,000 millimeter, and you can convert it there. So you get 1.05 times 10 to the minus 3 meter. And then the area, right? You know the area, after you work out the area, can remember, you work out the area by adding each section, right? And remember, the circle is a negative area. So if I ever say that the circle is a negative area, so you would have subtract whatever area you got for the semicircle. You'd have the semicircle area and you'd have the rectangle area. But the circle is a void area, so you'd subtract it and you get the area to be this 15.392 feet square, and you can convert that feet square, so you know the conversion factor is up here already given to you in this problem, might not be given to you in the exam. So one meter square is equal to 3.281. If you square both of it, then you get the equivalent, what it is equal to. So the square of that is equal to the square of this, and then when you multiply it across, the feet square will drop out, left with only meter square. Right? So you can do it the same way if you want in exam. Right? Just know the how to your conversion. Go through back a little bit of that. Debrief yourself on conversion from imperial to metric. Right? That is essentially what is happening. Right? Especially this one here. Right? This is metric, but one is standard and one is they are deviated. Right? And here now, the volume, remember now, volume is what? Area times height or area times thickness, right? Because area would be represented, let me just remind you, area is equals, we call it either length times height or length times width, whatever, time thickness. So that equals to the volume, right? So it's normally length times width times height. And the height, we substitute the height here for the thickness. And right, so you can consider that whatever distance you get for your rectangle, you can consider one length and one your width, right? That's not a problem, right? And then you would use this area times the thickness, which you already work out up top here. You multiply it and you'll get it in, you get it the volume. So when you have volume now, you go to your density formula, and everybody remember that density is equal to mass upon volume. And so from that, you transpose mass is equals to rho times volume. Right? So the density, your density was given. So always give the density. So you don't have to find the density. We give you the density of material, and then you multiply it by the volume. So that is showing you going back to the first part we started in the course about conversion. Remember we did a whole long thing with the container, right? So that you can go back into that sheet to make sure that you remember to do your conversion. So that is 13.21, and you can look at all of these questions we have with conversion. And so you get the mass. So it's 13.21. So let's jump back and look at our problem. All right. So here we go now. So we went ahead and we found the area of the rectangle section to be 15, right? So that would be 3 times 5, you get 15. And the area of the circle, negative area would have been pi r square, which have been pi times 1 square, and you know pi is 3.142, so you actually get back the same value. R 1 square is 1, all right, so you get the area as that. The semicircle would be um uh would be pi r square by half. Is this figure correct or is there an error? Let me just check it. So the area would for the semicircle would be pi r square upon 2, so that will be pi times the radius will be what? 1.5 square upon 2. What is that? Work out. Did anybody go through the problem? 1.5 square times pi, you get 7.068 divided by 2.
Sir, 3.534.
Yeah, right. So it is correct. All right. And that is in feet square, right? Or square feet, right? And so that is correct. Then now you add all of this together. That means you would have subtract. So this you add the 15 and the 3.534, and you subtract 3.12 when you get that lovely figure there. So that is the addition of them. All right, so you had these, that, you minus that one, of course. And of course, we already established that your x bar for the center of the figure mapping down to here, x bar for everything, x bar for all of them, or x1 if you want to call it. So that will be x1, x2, x3, but they are the same in this case. Right? So both for the rectangle, the circle, semicircle, they are pretty much the same. Alright? Because they're at the dead center. For y now, your y1, y2, y3. So we had said to you that y1 was 2.5 because it's half of the height of the rectangle section. And for the circle is at the dead center because y bar you need to move from the center straight down to the origin. And that's the distance that takes you down there. So it's 5. And for this one, how did we get the 0.635? We so it's 5 plus that little distance up there, as I said before. Um, for the circle, the semicircle rather. For the semicircle is 1.5, so it would be, what did we say? 4 upon 3 pi. So it would have been 4 times 1.5 upon 3 pi. Check that value for me. Tell me what you get. Everybody working it? You get 0.6366.
Yes, yes, sir.
Right. And the 0.6366 gonna add to 5, right? So it bring you back to this figure. Right? Okay. Alright, it's nothing wrong to check the values. So it bring you up to that figure. Now when you finish that, remember now you need to find the y bar for the centroid. But generally you're going to need that one. So you go now, you multiply each area. What you want to call this, remember we said that this was what? Area 1, area 2, area 3. Whatever you want to call it that way if you want to switch. So you multiply your areas by each one of the distance. Multiply them by x. So that will be 15 times 1.5. Multiply the same minus 3.12 by 1.5. right? So you get minus 4.713. Then you multiply 3.534 by 1.5, you get 5.301. You go again and you take the area and multiply the y components, 2.5, you get 37.5. The same negative one. Now negative times positive 5 give you minus 15.71 for the y bar times area. And you do likewise 3.534 times 5, you get 19.919, right? And then now you had each column. Be mindful that remember that you need to subtract one of them. The circle is a void area, so it needs to be subtracted. So you got 27.801, and you minus that, you get 23.088, and then you add up the other one, you got 41. To get your x bar, you would have, for x bar, you divide this figure here by the total area, which is displayed here. So you'll get back to 1.5. So it proves that your working is correct. Then you do the same thing for y bar, 41.707 divided by 15.392. You get 2.709, which is you see there. So that's your y bar for the overall of the figure. And your x bar is 1.5, which tells you that your working is relatively okay. So it's a little bit beyond the center of the rectangle, just a little bit above 2.7. So that is good. Any question there before I move on? Body good with that now?
Yes, sir. Good.
Yeah, man. Now we see the working out down here. See the area of the circle. We see everything down here. Semicircle. Only thing that I needed to have done was to put the minus beside it. To remind myself that, remind you guys that it's a void here, but it's a negative here. Alright? That's yeah. So you can make note of that. I think a minus should have been really there, so as to remind the person that yeah, it's a negative here. And then now, what do we do? We show you how to get the y bar for the semicircle here. It worked out here, so it's 0.63 plus the 5, and that show you get the 5.63. So all the workout is there. All right. Here now, the next thing now, part C, it says you're to, what did part C tell you to do? Part C, so we have done right down to part C so far. So now we're going to find the inertia around the centroidal axis. All right, so it's different from the x-axis. So let's run into it. All right, so you go again, and you're going to find the inertia of each figure. You're going to find it of the semicircle, find it of the rectangle, but the area, all of the inertia of the circle, which is void, is minus. You're going to subtract it. So let's do the circle first. We have the circle first. So the circle, you go ahead and you look in your table to see what's the inertia of a circle, a semicircle rather. And everybody remember, it's going to be 1/8 pi r to the 4th. If you don't remember, simply just jump over to your table. Grab your table at the back of your thing. If you want to rip it off of the exam paper, so be the case, and you'll take it and you look it in your hand. Right? If you don't want to flip in every time, well, I mean, once you have the question and you can just bend the paper and you have it. So you see it here. Where is it now? So for the circle is this right here. See it here. A semicircle. So semicircle is y. You deal with the y component, or is x. X we deal with, right? Right. So it's x is here. So see it here, right? So here you have it, and they are the same. So, right, so there's no confusion. They are the same. All right. And note for the circle, same thing up here. 1/4 pi r. See them right there. So you just run to your table, right? And for the rectangle, see it up here, 1 upon 12 BH cube, remember? And sometimes they reverse the order when we're doing the y-axis. The H becomes, the B become where the H is, and they switch places, all right? Okay, if you remember that, I remember the triangle is one now that you always measure your,
Excuse me, sir.
yes.
Could you repeat that, sir?
Oh, I'm saying that for the rectangle, when you're finding about the the y-axis, you switch places between these. So in other words, I always say to the students that when you find about the x-axis, one thing that I would say to do, to remind you, oh, come on, but I always say, when you're doing it about the x-axis, considering that you're looking this way, right? On the rectangle beam, you're looking this way, because let's say that you have your y-axis there, and you have your x-axis here, argument's sake. What we do, we look this way. So if you find around the x-axis or the centroidal axis, which is this in this case, right? All you have to do is look that way. Now your B for the, if it is around the x, your B is this distant, right? And your height is the h here. See the h here, so your height is this distant. So that's why they have the formula here. So this is the breadth time height. But if you're doing it against for the y-axis, this is the way that you'll be looking. Because typically you're looking for a parallel axis. So if you want the axis that is one axis here, and you're looking for the next axis. Suppose this is centroidal axis is passed through with this distant. So this would be your x bar distant, argument sake. So this will be the distance between the two that is relevant to you. So this will be your parallel, this will be your y prime. And let's say you find it around the centroidal. If you find it around this axis here, the moment the turning around this axis, you would have to subtract any distance you have around this axis. But if you find about the y, you're gonna just use the y bar distance. Alright, but anyway, we're gonna come to that shortly and I'll show it to you. So they switch places. So essentially what we're saying here, this now becomes, so the H and the B change position in the formula. So you see it here, where the B is where the H is, look. See them there? And change position right here. Right? So this, so all you have to remember is breadth upon. So I normally say to my students is just to reverse the order. You know, yeah. But like you have to just know that little nuance with that part of the form. Right? So anywhere your base is always, I will still call this a base. And I just said to them, call that your height when you look that way. So you know that orientation when you look. So I choose that way to say that's the best way to remember it. So you're always looking for your parallel axis. In this way, you can see that if for the x, is that axis parallel to this one. So this will be x prime axis. So you see that? So these are, you have x axis and you have x prime axis, which the problem that we're going to do now is around these axes. Not around, the last one is around the y. Alright? But anyhow, let us move on. So for example, let's say that you don't get a conversion like that. You need to remember. So these are basic conversions that you try and remember here, guys. Alright? Alright. So just in case you don't get that. See, for the quarter circle, this is what you use for it. Alright? So let's jump back to our problem. So we're right here, and we see that it is 1 upon 8 pi r4 plus the area times d. Now your d here is what I want to focus on a little bit. So it is pi, and you put the area, the radius in and to the fourth. Now this now is the area back of the semicircle. Remember, semicircle had a area to hit. Where's it again? Trying to find back. Where's the page with the area? So these are your areas that you're using, right? Remember, that's why you work them out. And this one is, the semicircle is a positive area, it's not a void area. And then now you're going to multiply it by d squared. So how do you get your d squared here? Watch it carefully now. So your d squared is around This one you find around the centroidal axis. Where is your centroidal axis? Isn't this your centroidal axis up here, so? See your centroidal axis here now? No, sorry. This is a centroidal axis right here. Pardon me. This one right here. Right here, so is your centroidal axis. So this would be your x bar in this case, because this is y. So this would be your x bar. Let me erase the first one for clarity. Hold on, going too fast. So the first one is not your x. So you're looking for an axis that is going to be parallel to the x-axis. Right? Once I tell you that, you look for an axis. It says passing through the x-axis. What it says now? It says an area about the axis parallel to the x-axis and passing through the centroid, right? So it's passing through the centroid. So it's your centroidal axis here. Yeah. So this is the centroidal axis. It's around the centroidal axis. So the body tend to want to turn around the centroidal axis. So you must find all the inertias for all of the figure around that. So what you're going to do for the semicircle, you remember that the distance was up here, 5 point something up here. Your y1 was right up here, so whatever your y1, whether it was y2 or whatever, your y distance was up here coming down from the bottom, right? I don't remember what did we have it as a while ago. So it will be your y3, right? So your y3, where am I? Everything gone? I thought I was writing right here so a while ago. Where was I writing? Gone? Well, coming back to it. Yeah. So your y3, this will be your y3. So it's your y3 distant, right? So your y3 distant there now, around the central axis. So it's this little distance you want. That is that D you want. D3. So your D3 is around there. Right? So your D3 square, which is this. So this is your D3 square. All of this. So your difference between the centroidal distance and that distance is your D3. Everybody get this right now?
Excuse me, sir.
Your Y3 minus Y bar. Give your D3. Hello?
This gotta be the y bar then.
Basically to be what?
So basically, I said the y bar off it, right?
I'm not saying that. I'm telling you something specific. So in this case, it's up here, you see the distance of the circle. Right? So you have to get the principle now, you know. We deal with the semicircle, and you know where the semicircle, why it's Y3 was.
Yes, sir.
3 is right there. Where is the centroidal axis? No, 2.709.
Yes, sir.
Rotating around that, so it must be the distance about that. So it's that distance they're using for the radius to get the rotation around it. So every figure going to rotate around this axis. You get the point?
Yes, sir.
Right. So the y bar, so that will give you the distance, and then all you do is going to square it and multiply it by the area. So you have to square it when you finish get the y distance. So you square it and multiply by the area. So you square it, and then you get that value there. So you get a positive inertia, and that's simply how you get the inertia. All right. Let's go now about the rectangle. So let me clean it up again. Because we just clean up each time. So that was the semicircle. What about the rectangle? So the rectangle, the same axis would exist. Alright? Same, it's pretty much the same axis. Oh, come in, trying to get it right now. 1 second. Alright. So this is your rectangle. This is your area of focus. Alright, now, not the semicircle. And so you would look for your y. What was your y? What was your y2 distance? No, the semicircle was y1, right? Remember whatever we call it. I think it was y. What were we called in this figure? Just use as a point of reference. Yeah, it's our y1. So is your y1? Your y1 was equals to 2.5. You remember that?
Yes, sir.
Right.
Yes, sir.
And then the centroidal axis is higher than where your y1. So they have a little distance. The distance is a small distance. It's gonna be your D that you're looking for, your D2. So your D2 is going to be between these 2 points. That's your D2. Right? So your D2, so your centroidal axis is higher than the one for your figure, but it's going to rotate around. That's a radius of which is going to tend to want to rotate around the axis of around the centroidal axis. So see it right here. So this is it. That is your D2. That small distance there. So it's the area of the figure times that D2 for the rectangle. And then now, of course, you would have used your standard formula up here. So the first part of the inertia of each figure come from the table. The second part is if you have to find if it have the parallaxis rule. That if it doesn't go through the center of the figure, where when it goes to some of them, if it's not certain you call symmetrical around the center, it will have this parallel axis theory will follow. So this is a parallel axis theory, you know. So you always have to be looking for a line that is parallel to the other one. Right? So some parallel axis theory is the principle that it is based on. So the area of the figure times that little D2, that little area right here, so that little distance. You get that D2. And so look at this one. For the rectangle, this would be your breadth, and the total height would be your depth. I choose to use depth. I love to use depth rather than using h. Yeah, some books use depth, some use height, and I'm comfortable for here. I always say the depth. The depth of it, D3, right? And I think they're probably related because centroids have to deal with also fluid power, you know. When you're doing fluids, you will get into some centroidal thing about especially for dams and all of that. Centroids and inertia comes in very well in fluid mechanics. So maybe that's why they use the depth. So probably I shouldn't even really use it in the standard formula. Probably should stick to the H. But anyhow, it's relevant. So we call that distance there. And in the water, they'll call it depth. Think about it, yeah. So here, yeah. So it's BD cube upon 12. So remember that frame of axis. So if either which you want to use BH cube upon 12 is the same thing. All right. Go to your table, you find that. So these are table formula. Likewise this one. And so you get that. What about the semicircle now? The semicircle or the circle rather. The circle for that one now. So you go to the table and you get the standard form, which is pi r squared 4 r upon 4. So let's go to the table for the different figures. For the first part of the inertia, the last part is always now going to be the area of the figure. And in this case, it's the area of a circle, right? Which was what? We got that to be some figure there. What was it? So see it here, minus 3.142. So this is a void area that we calculated. Remember, I put void area, means a negative area, right? And then now, you work out the first part, you will get that. And this is the area, which we just say is approximately pi. Now this one now, how do we find this part here for the D? This is your D1. Your D1 would be from where the center of it lies. This was 5, remember? From here to down here was 5. Right, so that would be your D1. No, that would be your Y1. Your Y1 for the circle was coming all the way down to the x-axis from the center of the circle. And so it is a difference of 5 from the centroidal distance. So essentially, this is your your D1 is this distance. Let me get a different color and show you your D1. Your D1 is going to be this distance here, from here down to where this distance right here. This is your D1 distance. So it's rotating. The circle from the circle is rotating around the centroidal axis. And the centroidal axis is this axis right here. Blue line. So that is a centroidal axis. Alright? So you notice the difference. And that's the key difference here. And so we have the minus area there. And so you go and you'll be adding that value, this value, and you subtract that one, and you get the total inertia down here. So that what we're saying there, see here. So inertia 1 plus inertia 2 had the last inertia you subtract and you get 46.908. And remember the unit is feet to the fourth. All of these values here. All of these values here you must get to the fourth. And you add the two of them and you get the final one to the fourth, feet to the fourth. So all the units are always going to the fourth power. Right? So when you add that one, fourth power. This one, fourth power, you add them together. And the same thing for the others. All right? All right. Any question there before we move on?
No, sir.
All right. Let's jump to the next one. All right. Seems like I'm going backward rather than forward, right? Where am I going? Okay. So it means that okay. So let's go to this one now. This one is part D. D as in dog. Alright, so that was part C. I think this was part C. I think the slide just mixed up. This is part C. Alright, so this is D now. And this one now, look what it says. Determine the moment of inertia of this area about the x-axis. It might be a little bit different in the slide that you have. The wording might be a little bit different. It's the same thing. So we find it about this axis. About the x-axis. You know the x-axis is right down there. So in this case, the first part of the formulas would be the same. Standard formulas for each section. Standard formulas goes. You look in your table and you'd have them already. In fact, you'd have worked the first part and these parts wouldn't change. It'd be the same values. All right, for the last part, the values will change. Same areas, of course. Same area, but the value will change. Let's look at it now. So for the first one, for the circle, the semicircle rather, this will be your bar up here. This is what your y, whatever we call it. What's what y3 would you call it before? Your y3 would have been all that distance up here. So 5.6366. That distance up there. It's above 5. Right? Now, if you find around the x-axis, that's the distance you use for your D. So your D is this distance. Right? Your D3. And you square the D3. So that's your D3 value. Right? Any question there? You see the difference in this part? It's still inertia you're finding now, remember. But we around which axis this time? The x-axis. Make sure you remember when you find around the x different from the central axis. So we're not this one again. It's down here. So we're finding each one of them tending to want to rotate around this axis. So it is going to be that y bar distance you have for your table. You just take it and you go square it and multiply by the area and you get that parallel axis part. So the axis that is going to be parallel to this axis is which axis? Is the x-axis. And you just use that distance there. So that's your y3 is that D. So your y3 becomes D. D. Right? You understand me now? Around which axis you find it? When you find it around the x-axis, your y3 becomes D. Alright, so let's move on. And you simply add these and you get a value there. What about the rectangle? Rectangle. What was your y1 for the rectangle? Wasn't it halfway the rectangle? And that would have been your y, what is it? Y1. I think that was y1 from our table. That's using what we had for a table. So it was your y1 and it was 2.5. Remember? That y1 there was 2.5. So that is now becoming your D because this is a distance that you need to rotate around the x from the center of that figure. So see there, 2.5. Make note of it. So that becomes your D2. Right? And similar for the circle, what's the value? It must be the 5. Because that's the center that carry down to the origin for the circle. And that was 5. So your D3 down here, obviously, is 5 also. I think, was that D3 or D1? I think it was D1. your D1, this is D2, and that's your D1. That's referring back to your table, right? So see, there is as simple as that. So there are two distinct things that I'm showing you this afternoon. One, when you're finding it around the centroidal axis, and when you find it around the x-axis, I could also ask you around the y. If you find it around the y-axis, this would be the axis that you're using. And all of the figure distance from the center to that distance is what? If it's a y, like what the question asked you for, it didn't ask you for around the central axis, it asked you for this distance. So you will look for the distance from the center of the figure to that line there. And that will be your radius that it want to tend to. So listen to me. Your D3 is like a radius, you know. It's the center of the figure rotating around some axis parallel. So with the axis that we're concentrating on in this case is from the center of each figure to the x-axis. Because that is around the axis, I would say you must find it around, not the centroidal one this time. Around the x-axis. So you go from the center of the figure each time, the center of the figure. So you see a D, that would be what? What that one was, this was your D3. So see them there, those are all the distance that we need this time around. So for each one of the figure rotating around the x-axis. Is that clear? As opposed to this one around here, where we're finding them around the centroidal axis, which is this axis up here. We call it x prime axis if you want to call it that. So it's right. So that is the centroid. Where the centroid is, it rotates around the centroid. So you have to take, you actually subtracting this from the you use the centroidal distance from each one of them, subtracting. So that difference will give you the radius. So you don't have to worry. It is as simple and straightforward as that. Please make sure you go through the slide and you're observant of that differences. All right. The question asks you about the y. I didn't work it out. I was just highlight the amount of inertia around the y-axis. So if you're doing it around the y, I'm just gonna ask you to tell me how it's done. I'm not going to really let me ask you. I'm gonna take the figure and I'm gonna ask you to tell me how that one done around the y. Let's see if we can copy it and we can go zoom and all. Let's copy it and we're gonna go there. Let's copy everything here. All right, and you're gonna tell me quickly how that one is done. Let's come out of this. All right, where are we now? Let's go into this software here. You're gonna have to give me a minute. I'm gonna step out 1 second. You're gonna give me 2 minutes while it's open. I'm coming back. Just look at it. I'm gonna paste it here until I get back, and then we can start it. So y'all can see it. You can start work it out now. You find it around there. Which axis are we finding around? But remember?
Why, sir?
Around the y.
Y,
So
sir.
work out the y while I looking for the question. Around the y. Right. So we're doing it around the y. So here we have it. Right around the y. Right. So it's around the y. So start work it. I'll be back shortly. While you think on that. Start work it. I'm coming. Give me a second. Okay. I forget to pause the video. All right. Anyway, you're all finished now? I suspect everybody tried?
Still trying it, sir.
All right. I'm ready to let's start it. While you prepare, you start it. Let me just see if I can get all of my tools. All right, I don't want to make the figure too small. All right. Okay. And I put that here. It says E. Yeah. All right, that's, come on. I want it up there. Oh, keep coming down. Why is it jumping over? Escape. All right, cool. Escape 2 times. All right, yeah, that's where I want it. So that's it. So we have some space. So let's go. So we have our information in our table already, luckily. So we have a head start. So now we want to take which one of the inertia we want to start with first. So we're gonna call this 1, as we call era 1. Oh, I don't have a writer. I don't. So we call that era 1, era 2, era 3. All right, in the order that we have it right in front of us here. So this would now become our y1, y2, and our y3. This become your x1, x2, and your x3. All right. So now which way are we looking? So our line of sight, our eye will be looking that way. All right. All right. So I remember say eye looking that, you're looking that way. You want to find around the y-axis. So the first one, for the rectangle, your inertia for the rectangle, right, is going to be equals to, and this is our rectangle, it's be equals to b h cubed upon 12, right? That's the first for the figure. So that's for the rectangle, right? So this is your rectangle, right? This is right across here, right? Plus area times your d1 square. All right. Now remember, these things are going to switch around. If this was your b down here, right, and this was your h, argument's sake, that's what, if you use it that way, your h is going to become your b, and your b become your h. So it is going to be h times b cube upon 12. So they switch places because look, this is now becoming your h. So your h is gonna switch place with your, so this will be like your base, and this is now your b become like your height. All right, so them switch places. All right, so you have to switch them around. You can't use it as in this form. All right, so you switch it to that, and they switch places. All right, plus a times d1 squared. So let's just now put them in. All right, so your h is going to be 5 times, what's your b now? Your b is going to be 3. So it's 3 cubed upon 12. But you agree with that? Any question
Yes, sir.
there?
No, sir, no question.
All right, the next one, your area now is what? 15. All right, what about your D1 now? Your center of it. It so happened that all our Our
1.5.
is 1.5, right, because it's the center of the rectangle. Luckily, in this case, this is your D1, right? So it's from the center of the figure. This is the center of the figure mapped to the y line. Why? Because that's the y-axis. So the center of the figure. It's not have to do anything with any circle or anything like that. So it's going to be 1.5 square upon upon nothing, sorry. So 1.5 square. All right. So that's it. Work those out. And the unit is going to be the fourth to the feet fourth, the fourth square root. The fourth square. All right, the fourth root, sorry. All right. Anyway, next one. Let's see if we can work the next one now. The circle now. So the inertia. For the circle. All right, so that's rectangle. This is the circle. What was the circle again? As a first inertia. If you don't remember, simply jump back to your table. Let's peep over here in our PowerPoint slide. So for the circle is 1/4. Right? 1/4. Can you see it? Are you seeing it?
Yes, sir.
Okay. So see here. So it's the same y/4 r squared. So let's jump back to our where are we? Here. So we are right here. There's 1/4 pi r to the fourth plus a times the d2 square, right? All right. So this one is going to be 1/4 pi. The circle radius is 1, so that's a given to the fourth. All right, so that's simple. And then the area is going to be 3.142. And if you notice, I don't use a negative area there. I use the area of it. All right, actually getting the inertia of the figure itself. And times d, what is your d now? Same figure. Say 1.5 in this case, because the center of the circle to the y-axis is still 1.5. So you use it. Is it so? Yeah. 1.5 square. Everybody agree with that?
Yes, sir.
Good.
Yes, sir.
So that one work out. All right. The next one. So you can work those out in the meantime. The next one also the semicircle. So I semicircle. Or I should put SC rather. So for the
4 to the 8.
pardon me?
Pi r 4 over 8.
No. Over 8? It's over 8. 1
Yes,
upon
sir.
8. Yes.
Yeah, over 8.
There's 1/1/8 pi r to the fourth. Right? Plus the area times d3 squared. I just put these just here just to show you these, relate these in the tables. I call them d3, just relating them to the table. All right, so this is 1/8 pi, and the radius is 1.5 square to the fourth rather, plus the area was what now? 3.534. All right, what is your D now? Your D happen to be the very same value. In this case, luckily, it's the same value. So it is D, your D square is same 1.5. All right? Now remember, the only thing that this value is minus up here. So remember that. For the circle, it's minus inertia value. So I put that in red.
Yeah.
All right, now. What's the first one?
Hands go say, going. What's the engineer?
But,
You ever try deep sea? 45. Deep sea.
Pardon me?
Up. 45.
Somebody is talking in the group. Who was open
Mute.
their mic?
Yeah,
Missing the meeting.
right.
Who is talking to me? Who is talking to me? I need to know who to mute.
Mute, sir.
Oh, the person who is talking is fine, but nobody else can beside you talking so that they disturb the meeting. All right. Okay. Next one. So the first one is what? What you say the first one work out to be? It's going to be
300 and
that is 3 cube 27 times 5 divided by 12. You get 11.25, and that is feet to the fourth, right? The fourth feet to the fourth power, feet to the fourth power. How much the other part come to now? It's going to be
33.7.
1.5 square times 15. How much you say that is? 33.
Yes, sir. 33.75.
Add those two values for me, please.
45.
45 flat. Wow. To the fourth power. Remember, it's to the fourth power here, guys. All right, find this one for me now. No? The first one is going to be pi divided by 4. That's so easy. And that is going to be 0.7853 9 if you want to be, plus, what's the last one now? 1.5 square times pi. So that is 7.068 6. What's that value here now?
7.855.
Minus, okay, so it's minus 7
Minus.
7.85 39 or whatever.
So, question.
Yeah, go ahead.
The area in the circle, the 3.142. Why I say you never put as minus again?
No, you don't put it as minus there. Yeah, when you work out the entire figure, you don't put it as minus. What you do, you work out the inertia of the figure, and when you finish work out the inertia figure, you use the inertia value as minus. The overall inertia as a minus value.
And that works for all cases?
Yeah, pretty much. Yeah.
Okay.
Mm-hmm. So you just finding so in other words, what you do, you find the inertia of the figure itself. And so when you finish finding the inertia, you use the inertia value as minus to complete inertia value. Once it is a void area. Right?
Okay, sir.
Right. All right. And then for the semicircle now, work out that one. How much is that now? That is 1.5 to the fourth power times pi divided by 8. So you get something like 1 point on a different color here. 1.988, right? Plus, what's the other part now? Other part would be, let me see if I can get this value here. 3.534 times 1.5 square. What you get there? So 7 point something, 7.9515. That's what you got?
Yes, sir.
That's 1.988. And so this one is roughly 9.9.
9.94.
395 or something like that. Right. And then now, so the total inertia total is going to be equals to IR plus TSC minus T circle. So what we have here now, it will be 45 plus 9.9395 minus 7.8539. How much is that value? Give me that value. Not working though. Somebody work out and give us the final figure. Please.
So I thought, yeah, decimal place is different. One second.
Yeah, give me, no. A 3 significant figure is all right. 3 sig is all right for the final answer.
So answer is 47.036. I'm sorry, 086.
086 says, it says 9 then. You can round off to that if you want. And that will be to the 4th root. Alright, so that's what you're saying that you got for that value. Looks pretty much correct. Alright, so that is the inertia. And around the what? The x-axis. Right? So you mean you're looking from a different way
On the Y.
and right. And so
Y,
the
sir.
2 parallel axes that we're concentrating on a while ago was this one. That's the Y. And the Y prime axis would be this one, running right through the center here. And you know why this is? It is symmetrical around the Y axis. The figure is symmetrical around the Y axis in that case. You see, if you were to find the inertia around the centroidal axis in the Y direction, you know what would happen though?
You would be
You can tell
0.
me what would be the value. What would be the value here? Just looking at these figure.
The value would be for the first one, you would get, right, let me see, rectangle. Is the rectangle, you get 11.25 feet.
Exactly. Yes.
And then
And
the
then the
second
circle,
one will be 0.78.
753.
Yes.
78, yeah.
And for the other one, what would happen?
1.988.
Yes, because it's symmetrical around here. So the AD then would drop out. Yeah, because you can't find out. There'll be no distance. But because the XC bar would be the same distance. You'll be subtracting the same 1.5 from 1.5, so it'll be 0 for all of them. Alright? So that is one of the easiest questions. I must consider setting this as an exam question and ask that question. Because it's an easy mark without much. Once you recognize that, you don't have to work out anything more than write back the original ones. You know, this is a nice question to put a half part to it and just ask for all of these plus that. And all the students have to do, once they understand what is happening, when they look at it, they just quickly write down all of these values here right before and have the answer. So that would be, this would be finding it around the centroidal axis. So if you're finding it around the centroidal axis for the Y, right? Using the Y axis as a reference, that would be it. Right? Right, but you'd have to be using the Y axis as reference for the figure in that instant. Right, looking in the Y. So there'll be no parallel distance there. So it will just drop out. Right? So it's in other words, I would have to say a moment of inertia around the centroidal the Y centroidal axis or something like that. Yeah. Yeah. So that you know that is the y1 you're referring to, not the x. Right? All right. So I hope you all understand that question now. With any form and shape that they come, right? Um, so right, that's pretty much for that case here. So those anybody understand those questions? Those questions will be a big giveaway. Let me just I can look back at another one. Just quick recap. Person, if you have a one that is a different shape, let me just look for another one. So centroids, inertia. Let's see. Let's look at if we can find another figure to look at. See if I find another one. So look at some people like this. I think I had share a slide like this. Oh, you got this one in some time ago. All right, but this one here, so I'm not gonna go through that one. Let me just show you this one. So for this one, it says determine the first moment with respect to the x and y axis and the location of the centroid. So you typically there's some trick to this one here. You have to be careful. So in this one, you have a similar figure like what I have there. Of course, you notice that down in the x in the y axis part go down there. Right? So you have to go ahead and you look, you see where your y-axis is and your x-axis. So some of the component for this triangle, a part of its y distance is going to be down here. It's y1, right? Coordinate is going to be down here. Look. So see if you separate it into a rectangle, triangle, semicircle, circle. Look carefully what is happening here. So for the triangle, you're able to see them clearly. So this is your y1, this is your x1. Back to the original. So you're always mapping them to the origin, right? Right here. And for this one, similarly, look at this one now. This is minus. And the 1/3 rule follow here. So it's 1/3 of the base. The base of it is 120. 1/3 of that is 40. So see there, from the back down, right? So up here says 80, but this is 40. So the 40 for the x, and for the y, what's the height here? This is 60. So 1/3 of 60 is 20, but this is minus 20 distant that. See there? Not positive 20. So that is your y2 there. And you see your y1 here is 40, while this y2 is minus 20. Look at the semicircle here now. The same rule apply with that formula there. Alright? And you add the difference, the 80 to that distance. So that becomes your y2, y3, sorry. And the y4 would be simple 80. See there? See y4 there, right to the center. Just like the one that we did before, it's right to the center. You have to map it to the center. But the distance here from the center is 80. Right? In this case, right? Yeah, and this also is 60. That's 60. These two are different. This is the only different one. Right? But everything else, the rectangle is 60 for the x. So your x1 here is 60. X2, x3, sorry. This is x3. This is x2 is different. And your x4 is the same. So if you notice, those are the same for your x distance. Right? I don't think we work out this one. So you'd have to go ahead and find the inertia. I think I have the slide somewhere now. Complete. But this is just a location. So you must find the first moment with respect to that, and then locate the centroid. I don't have it. Oh yeah. Oh, see it here. So it's actually work out here. Right, right. So it says here, so it's simple. We go through and we work out the areas to them. So the semicircle is minus there again, same thing. And you do the same multiplication across. And you're able to find the x bar, y bar after this. I think that you have this slide somewhere there now. I don't know if I'd shared with you. But right, so you simply do those, add the areas. And if you notice here, this minus one here for the rectangle, this value here is going to be the y times the area, right? The y times the area, right? The y times the area. Where am I now? Where am I? The y times yeah. So the y is gonna be times the area. The area is this value. The see it here is minus. That's the only minus one there, away from the circle. That's the void here. So that included. So that's the only difference there. And you just work out them the same way. So you're going to divide that into all of these and you get x bar and y bar value. And right. So that's how it's done. Right? I'm looking to see the workout here. So the central location, you divide this into that value, you get 54.8. And this one, you divide this here with this value here, you get 36.4. So that show you where your x bar and y bar really fall. And then you just go ahead and do your inertia. You remember the semicircle is going to be negative inertia, right? You work out the inertia of this one, that will be a solid inertia. Right? And just use the values as is. Right? That one I don't want you to see that. You have to, I think you probably have it somewhere there anyway. Right, so right, so those are, let's run to my last question. Right. I'll just run to my last question. I'm going to discard all of that. All right. Let me see. All right. So we're gonna go to one question now. We're just gonna look on the solution of it and how you need to approach it. If you get something like with any question like this. So, all right. So this is a question. I have this solution too. Let me just put it somewhere where we can look at it. Put it back on here. So you can actually have it. I'll put it on a new one. Oh, don't like when it start to run. All right, so this is a question. You should have done this question by now. Some of you will be familiar with this question. I think I'm going to I'm marking right now, and I will see who do it right, who I'm not. So this question here, I know I gave it to you to do, right? Right. Okay, so this is a question. Trying to make sure that we can see the page there. All right. So you're asked to do a number of things here. Why is this thing not showing up here? All right. I don't know why this thing come on the page here. Okay, I think it's, oh Lord. Okay, hold on a second. I have to redo it. I can't see the question. Hold on a second. I hope that's better. Let's try it again. I'll probably have to discard this one. Wow. Yeah, this is a question. How many of you worked this question already? Saw it on the worksheet. I know it was on the worksheet. Who remember doing it? Did anybody try it? Hello?
Different question like that.
Don't think
Yes,
we
similar question.
I put a question like this on the paper for sure. It's similar. I don't know if it's exactly this, but it's similar to this. It could
So I
be
did
the
a
same
similar
one.
question today.
It could be the very same question. Let me get a PowerPoint. Oh, I'll just use the Zoom now. Let me go back to it.
Oh, sorry, it's similar, and I same question, but it's similar.
You sure? You know, let's see.
Sure, because the forces were, I think it was like 60 and 70 for the actual forces. So the force them slightly different. I think the distances are off.
Okay. All right. So for this one, let us just discuss it quickly. So what happened? It says here you have to calculate the position vector of 1 second. So you must get the position vector of OA. Where's OA now? Let's see if we're seeing the figure good. Let's come down a little bit more. OA, see O here, and see A here, right? So you have to do OA, and you have to do, so we can actually write over here. So we need to identify, so we know O already, O is the origin, so all the points are 0, 0. We need A, right? Typically, that's how you operate. B, C, right? So you typically just identify those points first. It wanted to just get position vector. Everybody remember position vector? So you get the, so you know what? O is the origin already, and A. What is A? Tell me the coordinates of A.
So 0, I, 4,
Just give me the
J,
points.
and
Don't bother put them in I. Just give me the point where A is
0,
on the thing.
4,
And
and
3.
3.
0, 4, and 3. Let's check if you're right. So so the Y is 4 and X is 0 because right at the origin, and the Z is 3, yes? And so you start, just get the coordinate points. Don't start writing them in higher and thing yet. And B is going to be, what is X?
1.5.
Good. And what is Y?
0.
Good. And what is Z?
6.
6.
Okay, good. All right. And C now,
-2.
X is -2. Beautiful. It's behind the origin, going in the negative x-axis. And what is Y?
0.
0.
Beautiful. And Z is?
4.
Beautiful. So you could go ahead now and write anything you want to write. So OA is going to be really equal to A minus O. So it's really A. So it's actually 0I plus 4J plus 3K, right? And what else do we want us to find? They want us to find
A, B.
A, B, which is going to be B minus A. So you just simply look for B, which is 1.506. And A is already 043. And see, this one done, 1.5I minus
Minus
4J
4,
plus
minus
3K.
plus 3.
Right. So you get the position vector there. So quick. How much you get some mark there? 1 mark already. And AC, come on, thing. And AC now would be equals to C minus A again. So your C and your A. So C is minus 2, 0, 4, and A is 0, 4, 3. So this gives you minus 2I minus 4J plus K. Right. Right. So that gives you your position vector. What else did I want from you now? So you have to express the tension of each cable in Cartesian form pulling on A. Can somebody tell me how you do something like that now? So they say they want the tension in each. So you see the tension. The tensions are going from which direction positively? So you have a tension in AB, right? And you have a tension in AC. What they want you to do is get them into Cartesian form. How do you get that into Cartesian form?
Would you times the
Unit
force
vector.
times the unit vector?
Force time unit vector.
Because it says force, so it's gonna be the vector is going to be the scalar value. So the vector value is going to be scalar value times the unit vector of the line that the force is in. So that will be AB if you started with AB. Oh, that is B. So what's the unit vector of AB now? How you find the unit vector of AB?
AB over D.
So it's going to be 1.5 I minus 4J plus 3K upon its modulus,
Square root
which is
of
1.5 square plus minus 4 square plus 3 square, and you take the root straight. So no long thing, all right? And you simply write it back, all right? You can do it in 2 or 3 steps, and you get the modulus of that. What's the modulus of that, guys? So that would be 1.5 square. I don't have the solution in here. I have it, but I'm not looking at it. 1.5 plus 16
5.22.
plus 9. That's the root of that. Give you 5.22. Don't write 5.2. Try have a little leeway. At a 4, ideally 4 sig fig is good. Give you a good accuracy. Don't just jump and write the 3, because you're shortchanging yourself from an accurate workout. So the first one would be what now? It would be 1.5 divided by, give me the first one, work it out. 1.5 divided by that.
So 0.2873.
873. All right.
Is it for
All right, good. All right. And the next one would be 4 into 5.22 into that one. How much is that?
so 0.7663.
7663. And the last one?
2.45.
You mean zero?
Ooh.
Zero.
0.5747.
0 point?
Oh yeah.
5747.
Yes. Remember their value is always 1 here. So that will give you, if you're to square back all of these, you should get 1. You square back
No, no,
all
no.
of these decimal, you should get 1. So that's guided that is a decimal you're getting. So it's 0.5 what?
5747.
5747.
Yes, sir.
And this is J, and that is K. And then now all you're gonna do to get the vector of the force, right? You could actually write T, since it's a four. Well, you can write is F is alright. It doesn't matter for the what I said. It's tension, so you could actually write T if you want. TAB. I mean, you could change the formula to T if you so desire. So the tension is going to be equals to the 40. What was its value again? As AB value, it is 55. So it would have been 55 times it, times 0.2831. And if you're finding the opposite direction, you'd have to reverse the unit vector, remember? Because it gives you a direction, eh? Right. And then you multiply that out, and whatever you get would be your tension. And you do the same thing for AC, right? AC would be as AC value. You know, AC is peeping up on us somewhere up the top there. So your position vector RAC is equals to minus 2I minus 4J plus K. All right. And so your unit vector of AC similarly would be minus 2I minus 4J plus K upon the modulus of 2 square, right, plus modulus of 4 here plus 1 square. I take the root of it, and what you get for that. Can somebody give me that value, please? I want the unit vector straight. Let's give me the unit vector. When you do the modulus of that, what you'll get? What you will get when you square that part? So you will get 4 plus 16, that's 20, plus 1, 21, root of 21. So it's root 21, root of 21. You will get 4.58, what, 3? That's what you
Yes,
got?
sir. Before decimal place or 3?
3 decimal place is all right. 4
Yes,
6
sir, that's
decimal,
right.
3 decimal point is all right. How much you get here now? So it want to be first one, it will be minus. You know for sure. 0 point
Minus
something.
0.436.
I minus 0
0.873.
0.873 J. And the last one would have been what now? It's a positive now. 0. The reciprocal of that. 4.583 reciprocal.
0.218.
0.218 K. Alright, and it's similarly to find the tension in AC, you would see what was AC value again? 40. So you're converting it from scalar force to vector force. So it's going to be the vector, the TAC regular value, scalar value, that is vector, upon times the unit vector. So this is going to be 40 times that value there. And that is giving you all the pretty marks that you want. Straight go. You don't have to think twice. Just make sure you get the coordinate points right, please. So concentrate. I beg you. I beg you, I implore you. Make sure you concentrate. Alright? Concentrate. Alright, that's written a little bit close to that figure up there. That's why I put that there. So that's the tension. So remember, this is a scalar value times the unit vector. That's the formula. So you normally see F equals to scalar value of F, and the one done is written in dark and one written in light, and times the unit vector. That's beautiful formula is one that you use. Alright. So normally this one is showing that this is the dark one is in vector. And then they put the next one in a light one, you know. very light writing to show that it is a something like that. So it's a scalar one, scalar force times the unit vector. All right. So that's pretty formula one that I wanted to remember. And then now, the next one, next part now, they say that you have to find the moment of AC about B. AC going from AC about where? B. Who can tell me how to do that? Let me see if I get this a little bit smaller. How do I do that? I'm going to take out the figure again. Just the figure itself. And you're going to look at it and you tell me how to do it. We can always come back up for other stuff. Let's put it here. See if we can paste it here. Oh, it's big, massive. It's giving me such a big spread. Right. Yeah, how do we do this? Yeah. Can you see the axis that they want? So look. Oh, can you still see it? I hope so. Now, the axis that you want, it's about a point. They say it's about a point now, eh? So you must find about a moment about a point, yeah? Right? So the moment about a point, and the point that you find about is going to be what? This is about the point. Right, so you want moment about B is going to be equal to what now? So it is going to be R times F. Where is your position vector that you're going to use now?
B.
Pardon me?
BA.
BA. So you're saying your position vector that you want is BA. Uh-huh. And let's look back at what they want from you. It says here, find the determinant moment of AC. Oh yeah, they told you where you want. AC, yeah, AC about B. Says AC about B. Right? Says AC about B. So would you use the same thing? So let's just draw some lines here. And I get some color here. So about B, you have that line there going to the vector. So yeah, those are some of the things. So this is a line, and the vector is going to the line already. So this is your this is a line, one line connecting it. That's one of them. So you would consider that to be your R, eh? That is one. So which position vector would you use now? Are you seeing it? So you already know it's AC. Which distance are you supposed to be using? You see the distance, right? Well, what is the position vector? What's the position vector that you're using? You already know the force already. So you have the force. The force is AC force you have. Oh, why am I having this right here? I don't know. Okay. Oh, this is a shallow right here. Yeah. Oh, go ahead and tell me. Do you remember it?
There be a line touching the force.
Yeah, so you must firstly, yeah, the line must touch the force. Right.
So you can, in my case, you can use either BA or BC.
BA, 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 you said? BA. Why would you
Or
want to
BC.
use BA? BA is a
Or
force of
BC.
tension line. Right? I mean, yeah, it has a position vector too. It has a position vector, I agree. But yeah, it has a position vector. But if you're going to use BA, Yeah, you could use BA, and you could also, but it's about B, and you could use which other one?
BC.
Yeah, so it's your choice. So which one you want to use? See if it work out. Which one you want to use?
So you already have AB, so you can just flip it and get BA.
But why don't try to just use a position vector that is free from force and then just use a force with it? That's not another way to do it.
Yes, I'm just saying you already have A. You already have
So
AB, so just flip.
tell me what you want to do. Which direction you want to go?
I will go BC, sir.
So you would go. Let me write down a take. You're gonna tell me what to do. So you're gonna. I'm gonna see if what you are. So you're saying you're going what? What you say you want to go? BA. That's what you said a while ago.
So that yeah, one or two ways you can go. You can go BA because, as I said, you already have AB found earlier.
Uh-huh. You can go BA and what? But hold on. If you're going B, so you're going from B to A, time F. You say that you will go that way. Time F AC. Uh-huh. So the force must always be touching the line, eh? Right? So wherever so that is one approach. Which other one you say you would use?
Or BC.
You mean B
RBC.
RBC, going from B to C, time what? Time F AC.
Yes, sir.
Mm. So one you reverse the order, and one you turn the arrow that way. That's what you're saying to me. And one day you would turn the arrow this way. You would find. So in other words, you would have to reverse the order of your position vector AB to go
Yes, sir.
to that's what you're saying. Um. All right. All right. Let us look at the answer. All right. And the next one, how will you do the projection of the force AC along the line OA? Projection of AC onto this. How would you do the projection of AC? Where's AC? AC here onto OA. How do you do it? Can somebody look at that? Tell me how you do F? I'm gonna show you the answer for B shortly. But I just wanted to tell me how you do the last one before I go to that one. But remember projection? Always say projection is done again.
To find the position
Yeah, talk
vector
about
for
it.
the for OA. Wait, no, let me see. Projection force AC. So we find OA and then we use the moment for FAC.
We use moment? You sure?
Well,
You
it
sure? You
work around. So
sure it's
use
moment? Projection use moment? Projection moment?
projection. Oh,
It says
never mind.
projection,
Yeah. So
projection.
basically I do the same.
I want to
Do
be the angle.
the angle. Not the angle. The
Oh, then.
what do you call it?
I mean,
The force and
we
the
could
unit
ask you
vector
to
thing.
find. So look, a number of things question could be asked. We could also ask you to find the angle between. If you find the angle between AB and OA, you know, say it's a dot product you're using. Correct? You remember that?
Oh
Hello?
yeah.
You remember it's dot product. If we ask you to find angle, then it's dot product. If we ask you to find the projection of a force against a line, you need to find the unit vector of the line and multiply by the force of the line. You remember that?
Yes,
So
sir.
you find the unit vector of OA and multiply it by the force at OA, and you have AC already, because AC, you don't have to convert AC here. So it's the AC value here now. So all you need now is the unit vector of this line here, AO. But you notice which where they ask you from? From A going to O. So they want the reverse order. So you will get the negative of this. We never find, we have the position vector OA. See it up here, so 4J plus that. So it's the reverse of it. Because this is the one that you have is going from O to A. They want the one that is going is O. Which one they want? Oh, you have OA, but they want AO. So you have to reverse the order and find the unit, the unit vector of the reverse order of that position vector. So see it there, you get the reverse order of it, get the unit vector, and multiply it by this force right here. All right. Let us look. I think I have the sheet. Let's go on this thing here and look at the answer. So see if I can get to it. Scroll up. So all right. So all you do, I think this question should have asked some other stuff, you know. I don't know. Am I seeing the full gamut of this question here? Did I ask? Okay. You're supposed to find. Oh. Why I wasn't seeing all of this on that question? Oh, I actually skipped it. You're to find, we actually skip it and was discussing other stuff. So it asks you also about tension, the net force of both cable pulling on A. Right? If you ask for the net force, once you find these two here, you'd add the forces and you get the net forces. Don't? If it asks you about net force, don't you would add this force here plus that one there, the net force, it says the net force of both cable pulling at A. So if with the net force, you'll be adding this one plus, you're adding AB plus TAC. You agree? Hello?
Yes.
Yeah, so if it asks for net force, is the total force. So you had the two forces, if it's asking for net. And then you express them in terms of magnitude and the coordinate angles. So then, so you'll get the position vector, the Cartesian vector of the force when you add both of them. And then, right, when you finish this, you'll have able to add them. And then you're to find the coordinate angle. How do you find the coordinate angles? Anybody remember how to find the coordinate angles?
Yes, sir.
The coordinate angles, you would have got a tension when you add both of these, whatever values they work out to be. Can somebody quickly work out these values for me? What are those values? Quickly work them out for me now, please. Let me erase this for now. So give me the so the net force that is part C. Oh, didn't realize I'm jumping over the question. So part C, the net force, whatever you want to write it, T net is going to be equals to F AC plus F AB. Whatever those work out to be. But you remember you couldn't have them as scalar, but you can have them the vector form of them. What are those values, please? And the first one work out to be 55 times that plus that. And the other one 40. Can two person work them out quickly? So what is TAC for me? If you want to call them T. What is TAC, please? Just simplify those expressions there, please. Thank you.
1 sec.
Go ahead. Which one are you doing first?
TAC.
Sir, FAB, TAB.
TAB you're doing first.
Alright, so that's 15.565.
15.53 what?
565.
565. Just give me, okay. 5,
Yeah,
how much you say? So this is 15.53.
565.
So it's 7 is supposed to be then.
15.565.
So we can round this off as 7 then. You don't want to go to, yeah, you don't want to go too far up, too many figures, yeah? And,
So 57.
yeah, and then the next one would be what now? Minus what?
Minus 43.15.
43.15 J.
Oh, 42.15.
42.15. That's what you said?
Yes, sir. And then plus 31.61.
31.61 K. All right. And then the next one, hold on. And the next one, let me erase this. Actually,
Minus 17.44.
oh, come on again. So this one, let me get right here. It is TAC is minus what?
Minus
7,
17.44.
and this is I. And the other one would be minus
34.92.
34.92 J. And the other one would be plus what now?
8.72.
Okay. So the net force is equal to sum of them. So it will be TAB plus TAC. When you add them, add all the i's together, what you get? It will be 15.5371 minus 17.44.
Minus 1.
Hold on. Let me start that over again. I don't know. I have so much space and I'm going to run out of space here, so I can't. Let me clean that up and do it over. Let's write them again. Utilize the space wisely. So it is going to be your net force is equals to net force is going to be TAB plus TAC. So you sum them. So it will be 15.537 bracket minus 17.44. Alright. The next one would be plus bracket minus 42.15 minus 34.92 bracket J. And the last one would have been plus 31.61 plus 8.72. What are those working out to be now, guys? Give me a workout here. So one of them is going to be minus something. First one, two of them. What you say they're going to be now? This is 15.2, 15.5 minus 17.44. How much your value get there now?
Sir, 1.903.
1.903?
Yes, sir.
I. Minus. This one is going to be a big figure. That's what? 70 something.
77.07.
And the last one would be what now? 39.72 K.
40.33.
Pardon me?
40.33.
It's 40.33?
That the calculator, sir.
All right. Let me correct that. Yeah, it's true because you have a 7 and a 6 there. So it's 40. How much?
0.33.
Yeah, you're right. You're right. Okay. So all right. So you have your tension there now, your net force. And the coordinate angles. The coordinate angles. I was asking how to find the coordinate angles. How do you find the coordinate angles now, please, for that net force? How do you find the coordinate angle? What is it asking for coordinate angle? And it's expressed in terms of coordinate angles. When you say coordinate angle, what do you do? What do you do to get the coordinate angles? Once you have a Cartesian, you have a force. So this is a total force. Right? How do you get the coordinate angles that this force represent?
So you find the modulus of the force.
Yes, yes. And you get back the unit vector of it. And from the unit vector, you get it. It's very simple. That's 1.903. I minus 77.07. Yeah, plus. Just get the unit vector of it. So you get the unit vector, which is be minus 0.903 squared plus 7 plus 40.33 squared. So you square those, take the root, right? You're gonna get a one figure. What those work? What you would get there? Get the unit vector for me now that represent. How much you would get when you square those? You get a big figure, I think. 27.03 square plus 40 square plus. And you take the root of all of that. You get what? 87. Yeah, so 87 dividing all of these quantities. Upon 87. So it will give you the unit vector. And it is the alpha beta of each u part of the unit vector. So it's alpha, beta, and gamma of each section. For the I, for the J, and for the K. Alright, what that is represent. What's it? Go ahead for me now, guy. So what's the unit vector?
For I, it's negative 0.022.
Negative 0.022. Negative
Negative 0.022.
All right, so that's your I. And what's your J now?
Negative 0.886.
All right, that's J. And your K is what now?
Negative 0.464 positive.
4. Yeah. All right, so your alpha is because alpha is equals to the minus that. Let me write that good. It's the minus of 0.022. That's right. That's represent the I, and then the other one would be cos beta. Sorry, not gamma. Beta would be for the J equals to minus 0.886, and then gamma cos gamma is equal to 0.4 6, 4. What's this one equal to? This is an inverse. This is inverse of this, but this is a minus. Make sure you put the minus there. It's very, very important. So it's minus 0.022. The cos inverse of that.
91.26 degree.
Right, so you get 91 for that one. 0.26, or you could just 91.3 would be suffice that. All right, but as accurate as possible. And this one will be the cos inverse of that one. What you get for that now? 6 cos inverse. You get something like
Say 152.37
1.4. Well,
or 4.
yeah, and then this one would be equals to cos inverse of that again. 0.464.
62.4.
62, yeah, 62.4. All right, so that is how you get the coordinate angles. Whatever vector you have, you find the modulus, divide them, and you get the coordinate angles. All right, this one here talk about determine the angle between two vector. Everybody know what that is already, right? So you have the two vectors. Remember, you have the two vectors. You would simply go ahead and you just work them out, work out part of one. So you have these two, and you actually have the values them too. So you went ahead and you found them. So you would multiply. So either you could just use a position vector. You don't have to use a force. You could use a force, but you have the position vectors. Don't? Which make life much, much easier for you. So let's just take the figure and we have this figure here with these values so we can work with them, right? So make life easy. Easier. You have the position vector already. So you just go down. Let's get another page. And you just tell me what to do. This is revision, you know, so you tell me what to do. And I'll write them. Do I need to carry on anything else? Okay, you work them out already. So you had AB, you had AC, we just carry that one down to right. I think we took it down. Oh, this one cut off. Oh, we can see it. 1.5 I. This was what? This was unit vector. What was that? I'm just trying to. Oh, that was a position vector. 21. It's 2.1. 2.1. Oh, see there? That's what we want. We had that. We had AB. So we have AB and we have AC. All right, so you have your position vectors. Just rewrite them again for clarity. So your position vector RAB would have been 1.5 I minus 4J plus 3K. And you have your RAC value, which is minus 2I minus 4J plus K. And all right, and your dot product is going to be A, B dot vector dot with A, C dot equal to what? The modulus of what?
AB times modulus of AC.
AC, yes.
Cos
Cos of
theta.
cos theta between them, because that is what you want to find. So cos theta is equals to the product of the two vectors AB, and they dot them, and you're supposed to get one value divided by the modulus of AB modulus of AC. Right. So that is simple, straightforward. It's just, and remember, so we're going to demonstrate it again, just for clarity. So it is going to be 1.5 I minus 4J plus 3K again times, this is very easy, all right, plus K. Now, as I said again, I times I gonna give me what? 3 right? Because the i's will drop out. Don't have to write them down. Then you're gonna go 4j times 4j, that is gonna give me plus 16. The j's drop out, and you go now with the k's now, so it's 3 times 1. Or 3 times 3k plus 1k gonna give you 3. Alright? So that is as simple as it. See here, done. Sign it high. So that is what's that? 22. So that equals to 22. Right? That is for the dot of the two vectors. And the modulus of the vectors, we worked them out already. What were they? Remember we found them already? We don't have to find them 2 times. You just look in your notes and you see that one was didn't we find them already? You did it now, but we didn't write them down, did we? One is 5 AB, no. Yeah, AB is 5.22. You remember this? Is R
Yes,
set
sir.
unit vector. Yeah. AB is 5.22. What was BC? Let me write it down. 5.22. That was AB. Can you find them already? You know, just go back and look. You find them already, you don't have to repeat it. So you just go and say AB, the modulus of AB is equal to 5.22. Right? And you know you need the modulus now of if you can't bother, you can just work it out again if you. So the other one, AC would have been minus 2 square plus minus 4 square plus 1 square. Right? What would that have been again? So that would have been 4 plus 16 plus 1. So it was the root of 21. Yeah, man. And you could have done the same thing for AB. Just say AB would have been, you could have this too. 1.5 square, whatever. What did we root to get 5.5? Let's can square that back. What did we root? So if you have it this way, you got 27. I think you got 27 for the right here. When you square them, you had something like 27 point 2. I'm just showing you if you still have the root over there what you could do. So you could still keep a root in just of time and just go ahead, put it in your formula straight off the bat. You don't have to even hurt your head. Let me do it over here for reduce the space. So it says cos theta is going to be equals to 22 upon root 27.2 times root 21. And guess what? Root times root is 1. You remember your indices? So you don't have to do anything. So see there. So root and root, they would so you could work them out there. I could choose to keep it until they work out the same way. You understand what I'm saying? Because 22 and this would be 27.2 to the half times 21 to the half. Maths on line up. So what you say you do, you're gonna add the index. When you add the index, you're gonna get 1. So then the root then will drop out. And you just multiply 27 by 2 times 21. And they're supposed to give the same I think I should give you the same thing. Let's check it. Same ratio. Let me just check it. So it's supposed to give you so it's the root of that and root of that divided by. They should give you the same thing. Anyway, let me use a root. Let me use a root for clarity. Not one, but I'll let you use it. Just right. It should work out. Just put them the modulus of them. So the value that you will get here would be what? 5 point. Let me get it right. 5.22 times root of 21 was what again? We found a while ago. 4.58. And what you get here? You would get 22 upon Let me see what is it that we're getting here. It should be 5.22 times 4.58. Alright, so you would get here like 23.9. Right? Alright, so what this would work out, you get a decimal here. So this would be equals to that will be times 22. Let me see. So you get something like 0.92. Right, so cos theta is equal to 0.92. Right? And so is the cos inverse of that. Anybody check the working? Okay, so it's the cos inverse of that, please. So it is the cos inverse of 0.92. It says 27, 23. Once that is correct, that is the correct answer. You can always double check it. Once you get the root of that and the root of this, that should be it. So you square that quantity, square this, right? And you should typically get those answers. Everybody
So
remember?
basically I get it.
You got the answer? The same answer?
If you use the square, the square root to 27.2.
Pardon me?
And if you use the 27, if you square root 27.24, I think, and the square root 21, you get the same thing.
Yeah, you should get the same thing. Yeah, that's it. Cause it's you're using indices, so it can't go wrong. You know, it look wrong a while. I don't want to carry wide, but it's mathematics. You understand me? It's indices, so it should give you back the same value. All right. So yeah, so you get 22. No, that I didn't use 27.25. When I check back the values at what it is saying, um, but we use 27.2, so you should get it roughly there. All right, so that is it. I want you to say when you multiply 22.2 times 21 and you do the reciprocal, you got the same decimal. That's what you're saying?
I just use the root.
Okay. All right. Let me. So you do that. Hold on. Where are we now in the problem? So we would have done this one. We had run down to moment and never do this. So, and then the moment part now. All right. So the moment part. All right. The moment part and the projection part. Let's just go through a slide thing that I have here. Let's go on and look at it. Right. So you would have had these, right? Once these are correct, you would have got through and work it out. It looks a little bit different. I don't know if we are changing the value here. May have changed some values here, but it looks close to it. The angle. All right, so we got the angles. These are close to what we got, right? Something like those. Yeah. If we check back the working. It look like the answers a little bit different here. Check it. I don't know if I made an error while doing it, but we should get. It says 16 here. Let's check that. How did he get 16 here? Let's check that. Let's check the working if I made an error there while calculating it. It says 16. Let's check back that product here. One of them was minus. Hold on.
Yes.
Oh, yes. Thank you. Nobody picked it up. 1 is minus, so the answer different. This is minus here. Because 1.5 times this is really
16.
is 16, yeah. So there was an error here. So this is, yeah. So yeah, the answer would be a little bit different. Let's do that over. Let's check back answer. It's good to look to review what you do. See if you made an error. So let's all right. So nothing wrong with that. Make sure you check back your thing. Just check it, just scan it back over to see if you have any sign issues there. And it goes through for your working in general. So it's really 16. Yeah, so it's 16 supposed to be up there instead of so it's 16. Yeah. I'll get a different value for the angle. So that will be 16 instead. Alright. So that is 5 times that one. So that's divided by so what that would give us now? That would be 5.22 times 4.58 reciprocal of that times 16. You get a smaller figure for sure. So this angle would be wrong. Let's correct that angle. Going too fast. All right, because almost 7:30. All right, so it is what's that now? You get something like 0.669, and the cos inverse of that. Oh Lord, this calculator, every time I touch it, it gives me something different. So it's something like 48. I think that was about 47 something. Approximately 48 is the angle. All right. All right. So let me quickly just look on the answer with you. Just discuss it. So you would go through, as we said, find those position vector, find the unit vector, multiply it by it, get the tension there. Can you see it good? Let me just make this a little bit bigger. All right, same problem. So we convert the forces to vector form, multiply the scalar by the unit vector. See them there, right? And then we simply add the tension. So tension 1, tension 2, and then you find the angle of that vector, the same vector here. You divide it by its modulus. You get the unit vector, and you take alpha of the unit vector. It means therefore that our angles up there, oh well, I didn't check that part. I didn't check this part if it's correct. Once we work out this part correctly, we had them consistently correct here. These two are saying that we have positive here. I don't know why. One of them is supposed to be, this look like there's a minus here. Yeah, look like there's an error right here. So you know, there's supposed to be a minus right here. So I think the minus drop off here. See here? There's a minus supposed to be right here. So I think that would have made the problem wrong. So the minus right here, and then
And the positive, sir.
pardon me?
And the next one should be positive. The K.
Which one? Oh, this. Yes. Sometimes tired and I'm typing up stuff. Yeah, make error. So it's supposed to be minus here. And then this is minus, and then this will be positive. So it may be throw off the entire thing here. So we can see spot some errors sometimes. Because I tell you, sometimes when you type in these things, it's an hard deal using softwares. So yeah, so there's an error in this part here. So maybe this answer here is not. I need to check it back over. Right. All right. So therefore, it means to throw off these angle here. I think the one that we did is correct. All right. The yeah, there's some typo there. So the angle you would find these. Yeah. So approximately that is correct. That product here is correct. So you dot them and you multiply the two vectors and you will get these. So see there, same values there. Now the moment, as we said, the moment of F about B. So you could simply, you have F already. and they have AB. We use AB right times that, right? Um, um, AB. I think this is supposed to be a reverse, you know. I think this should really reverse for AB.
Yes, sir. It should be BA.
It's supposed to be BA. This is supposed to be reverse. This order is supposed to be reverse. Time I'm tired, I'm typing, you know. It's supposed to reverse, yeah. This is reverse order. So you would have reversed the order of this and do it. So there's some error right in there. But the projection, you will get the unit vector of AC, right? And you multiply it by oh, this was a different one we're doing. No, that's not the correct answer. Yes, go back to where we were. So all you do for the projection, you would get the unit vector of this guy and multiply it by the one that they asked to get. So we know the unit vector of it already. What was this unit vector? Let us just work that one. So the unit vector of this would have been, so OA, but we needed, which one did they say we must find it to? It says AO, says reverse. So you do the reverse. AO was what again? What was its value? It was 4, 3, 4J plus 3K. So you take the reverse of it to get AO. It will be minus 4J minus 3K. And then you would find the unit vector of AO, which would be really minus 4J minus 3K upon this modulo. So that would be 4 square plus minus 2 square. That would give you what now? 4J minus 3K up on that would be what now? 16 plus 9, 25. So it's really 5. Oh yeah, I should pick it up. So therefore this would be 4 upon 5. How much is that? That is something like minus 0.8 J. And the other one would be what now? 3 upon 5, what is that? 0.6. So that's 0.6 K. So you get the unit vector to get the, so it will be the unit vector times the force. So the force is, we are the Cartesian of it. You could use this form, you could use that too, but since we have it, so you could either use the scalar form of it, or you could use the vector form. If the vector form you're using, you'll use this one here, or this. See it here? So any which one of you want to use, right? But means you could get the answer in 2 forms, right? Where am I? I'm just trying to find out where did I work out the position vector? Was it here? Okay. So the projection of the force as the last part, it could be simply written as 0.8J minus 0.6K times the 40, vice versa. If you work it this way, you're gonna get it in Cartesian, or so you just simply work out those. So no. All right, so that's one way to do it. Time 40. Calculator give me an error. All right. So that would be minus 32 J minus, what is 0.6 times 40? So this is 20, 24. Okay. All right, so that is one way to do it. You could go ahead and do it the other way by multiplying it by the vector form of it, right? So you get 2 different answers if you depend on the type, the approach that you have taken. But I'd prefer, seeing that you work it out already, I think I should tell you, I prefer you use this form, right? It basically give you about the close to the same thing. It should give you about close to the same thing. We could check it. We check it. What was it again? It will be minus 0.8 J, 0.6 K. And what will be the other? What will be the other one now? It will be this here. I have the tendency of making mistakes if you, so I just bring it down. So this is what you multiply it by. And I'm tired. So I'm going to be, all right, so today has been a long day. Here you go. So you'd multiply it by that. So this would be a dot product. Here, guys. That would typically be a dot product. So look, you see that the I 0. You see that? Because the I over here is 0. So I times that first one is 0. And the next one would be 0.8 times 34. So it's 34.92 times 0.8. So you will get something like 27.9, right? Approximately there. That's your J. And what's your K now? Your K would be 0.6 times that figure over there. So you'll get two different, if it depends on which form you use, you'll get the two different I prefer you use the vector form, right? It doesn't matter seriously, right? But that's basically how you do it, right? That is 0.6 times 8.72. What are you giving me? Error. 8.72. You get something like 5.232. Right. Yeah, so if you use this formula, you're gonna get this form. And if you use that one, because this one is considering that the scalar value is being multiplied by this here. Right? Right, because this is the unit vector. And this is right. Right, so those are projections. Remember, please read up on projections. Right? Read up back on projection. You can use this problem on the one we worked before. Put yourself online, and also the moment. So the moment you could use going BC, right? And you could also use this one here, going BA, right? So you must decide which one you want to use, right? Yeah, so it's your choice, right? All right, guys, I think I'm exhausted now. I wish you the best in the exam. Just go and
Sir,
yeah.
quick question. I sent you a message, Chad Lawrence, regarding the assignment. Is it still possible for me to